gate voltage. And these are IV curves obtained for different gate voltages. And what you see is like essentially we can measure the MAR, so the multiple Andreev reflection contributions of the Andreev states of this nanowire. So this is just to show an example in a very different system how the same formalism is involved. Okay. So one of the requirements here is also to be able to phase bias. So to phase bias, I will just I will just say that what we use is essentially a squid. So as it is clear from this morning, if we just take our weak link and just embed it in a superconducting loop, by threading a magnetic flux and by using the fact that the inductance of this loop is very small compared to the inductance of this weak link, we can just impose the phase difference delta that is dropping in the weak link. So we can just control the phase drop in the junction. So now a question is, how can we get a system in which we can measure the transmissions and at the same time measure the current phase relation? So the idea is, it's very ingenious, is to use a junction here. So this is a very asymmetric squid. In this case, the critical current of this junction, of this weak link, is very small, orders of magnitude compared to this junction. So this is a very big junction, and the idea is the following. So if the current that we apply here, so if this current is smaller than the critical current of this junction, in this case, this is just like a short. This is like a cable, and all the current goes through this weak link. So we can measure the phase relation just of this part of the system. On the contrary, if we apply a current which is larger than the critical current, this is like open because it jumps to the dissipative branch, and we can measure just the IV of this junction. So we have two, like a switch, like a on-off switch that we can play with, and this is the idea. So the experiment is look like this. So we have this. This is the squid. So there are many lines because a junction you have to fabricate with the shadow evaporation. So this is the Josephson junction. So this is aluminum dioxide, aluminum. Okay, this is just a Josephson junction, and this is the constriction. So you can imagine it's a hard fabrication. You have also to do this in a plastic substrate, which you can then bend and break to make the atomic contact. Of course, it can happen that you break your junction. It can happen many things. So let's show the experiment when it's working. So this is the critical current of this atomic contact is 30 nanoamperes, and this is very small compared to the 700 0.7 microamperes of this junction. So at V equals 0, at the large voltage, we can just measure the transmission as before. At 0 voltage in this junction, we can measure the current phase relation. So an example of this. So in this case, so the junction is open. So it's like an open here, and all the current is flowing through this atomic contact. And we can measure the I versus V, and we get, as before, the MAR contribution. Okay. From this MAR contribution, so we have 1, 2, 3 different cases, and in all these cases we get the transmissions of the channels. Okay. Then what we can do is just to go to 0 voltage. So in this case, this is just a ring, a squid, completely closed. This is just like a closed loop, and we can measure the current phase relation. And in this case, what we measure is the current phase. This is the critical current as a function of the phase. And in fact, it's very hard, as we said today, to measure the critical current. So this is the switching current. Okay, I can comment on this, but it's almost, in our case, it's almost the critical current. So what you see is that in this case, where the transmission is very high, one gets a current phase relation which is really non-sinusoidal. And as the transmissions go to a very small value, one gets something which is more sinusoidal, like a standard Josephson effect. So from this it's very hard to see, but in red there is a fitting using these transmissions, and the theory just with the equations I showed 20 slides before, and then you can plot this, and this gives a very good agreement. So there is a very recent experiment by Mourani made in Orsay in France. And in this experiment, I show because I like very much this experiment. So here, what they have is a bismuth nanowire. A bismuth nanowire, the idea is that in these nanowires, these are the kind of new materials, they are supposed to have edge states. These edge states, this is the simulation of the electron density inside the system, and they are supposed to have two edge states living inside the wire. So the wire is this. There are two edge states, and the idea is that in this system, these states are ballistic, are like topologically protected, okay? So this is what is expected. So what they do is a very similar experiment. So this is a junction, an additional junction, and this junction is just made by a constriction. And what they measure is essentially the critical current as a function. Well, so this is the critical current as a function of B through the loop. And why they put, well, okay, let's see what they find. They find really a critical current which is almost dans the C to CT. So exactly this in English. So just very non-sinusoidal, and which is what would be expected for something with transmission 1. Okay, but if you pay attention, there is one contribution, and there is like this shoulder that appears. They explain that in fact in this experiment there are two flux, because one of the channels is here and the other channel is outside. If you see, one is inside, the other is outside. So there are two surfaces, and the difference in the period between these two it's related to the difference of surface between the two loops. Okay, so this is, you can check I have to update the reference. I think it's already. So now in the end, what remains, it's in the last minutes, 10 minutes I think. I don't need much more. So I will just discuss the spectroscopy. So we have this very simple system where there is a weak link here, and the density of the density of states inside this weak link, it looks like this. So there is these localized states with an energy that depends on the phase. Okay, so which are the possible microscopic excitations? And this is a problem which I'm going to come back tomorrow. So the ground state of the system, everything that is below the Fermi level is occupied. Okay, so this state is occupied and all these continuum states are occupied. One possible excitation is to add quasiparticles. So one can come with a tunnel probe and add electrons. So just come with an electron, occupy this state. This is an excitation that costs some energy, which is EA. Okay, we'll have to pay this energy. The other possibility is to put a negative voltage, if you want, and then remove this electron. In this case, this is an excitation that also costs EA, this Andreev energy, and this is like adding a hole. In both cases, it's adding quasiparticles. In one case, it's adding electrons, and the other case is adding holes or removing electrons. So let me just to finish this characterization of Andreev states, let me comment on this experiment. So in this experiment, there is the weak link is a carbon nanotube. So here, what you see is a carbon nanotube. And this carbon nanotube is forming a junction between this superconducting electrode and this superconducting electrode, which are both close, like to form also a squid. And the idea is that once this is forming a squid, by threading a magnetic flux, it's possible to impose the phase difference. Okay, once again, one uses this idea to control the phase drop in the junction. What is here in red is just a tunnel probe. But in particular, it's also another superconducting electrode. So it's a tunnel probe of superconducting material. Normally, to do tunnel probe, one can use a normal electrode. In this case, the measure, the IDV is just proportional to the density of states inside the system. And if it is a superconducting electrode, there is a deconvolution. But the resolution in energy is larger. There is also here in violet, in purple, there is also a back gate to control the number of electrons in to gate the nanotube. So let's see what happens. So just a comment, Dimitri is going to explain this better than me. So the tunnel current, so there is, of course, what is inside the tunnel current. So you need to make tunneling of electrons, so you need to start with electrons occupying state, to go to states which are unoccupied, and to take into account the density of states of both the electron and the system. In this case, just to say, the differential conductance, when one measures with the superconducting probe, there is a convolution between the density of states that one wants to measure and a function which depends on the energy and the voltage. This function has all the Fermi levels, Fermi wave, Fermi functions, etc. So just just to say that here we can measure the IDV using this tunnel, superconducting tunnel probe, and we can deconvolve to obtain the density of states. In this case, it's just a detail, but it's important. And in this case, one obtains is this. So this is the phase difference here. This is the energy, the voltage. This is the energy converted into, so the voltage converted into energy. And this is in color, this is directly the density of states. So the convoluted, the EIDV, okay? And in this case, one see there is this phase-dependent states which lie within inside the superconducting gap. And this was the first observation of Andreev-bound states in a carbon nanotube. I think the first spectroscopy of Andreev states in any weak link. There is some theory. It's possible to make a theory which fits very well with just a single channel. But there are other features which I'm not going to comment, which would become very long, which are difficult to account, because in a nanotube it's very easy to form quantum dots and many quantum dots, and then it becomes a bit messy. So okay, so this is the end. So I stop here. I don't know if the time, but I think it's okay. So for tomorrow I will just use just the like this, like for a film. The présenté, how do you say for a film? La queue for the film. The advancements, I don't know, remember. So, advertisement, yes, for tomorrow. So I will use these two states to promote, to use, just to excite from this occupied ground state to an excited state. And in this case, the fact that these Andreev-bound states are far away from the superconducting gap, so they are excitations that really are not coupled to the continuum, and therefore they can live longer and they can be manipulated coherently. Okay, so this is for tomorrow.
Okay. Let us see how it was hard to understand. Yes.
Yeah, in case of supercarbon nanotubes.
Yes.
Now, the maximum current that is per channel. So you will have two quantum conductors, right? Correspond to quantum conductors.
Mm-hmm. It depends on the transmission, yes.
If you gate, let's say if you drive the nanotube to one of the Van Hoff singularity,
okay.
With that, you probably have a strong coupling.
Okay. Yeah, it's a good point. So I just for this for today I just presented this case, but of course these Andreev states can be followed as a function of the gate voltage, and it can be observed that the behavior is essentially dominated by the presence of quantum dots, and how the levels of the quantum dots are or not resonant with the Fermi level. So this is what was observed in these experiments. I think that in the case of graphene, you can go to more exotic cases where you see maybe these singularities. But
Okay. Some other questions?
yes.
First, I have a very naive question.
Yes.
And depending on the answer, I have a second or not. Aluminum is a S-way superconductor, right?
Yes, wait, yes. BCS. Very.
The second question is, I don't understand how the sign of the other particle can change in order to have a Andreev state in this S-way superconductor. Because to have the Andreev state, you need to change the sign of the other particle. But if it's S-way, how you can change the sign after the Andreev scattering?
So I'm just, so I don't know if I understand the question. I'm just, so the idea is that the two, to form these states, these bound states.
I mean, in the atomic form that you have, then you have a Andreev state, right? But if the superconductor is a S-way, I don't understand how
maybe you are,
the sign changes.
if I may point out, you are pointing out that in a D-wave superconductor there is automatically a phase change because of the presence of a surface, and then you create an Andreev bound state just at the place where you.
Yes.
So here you have a phase change.
Yes, here you need two electrodes. Yes. You need a phase first. Yes, there are no Andreev states in a single interface. There is a contribution of the Andreev reflection to the current, if you want, but there are no bound states. If you have a single interface, there are.
Well, there are bound states in the nanotube.
Yes.
Or in vacuum,
Yeah.
between two you have bound state. But I think probably it is because the electron and hole, they are not exactly at the same energy. So there is a phase shift that accumulates when it runs. No? It is not due to this. In an Andreev process, at a given energy different to zero, there is a dephase between electron and hole.
Yes, if in this no, but this contribute, we can discuss, this contribute for a finite length, you can take into account the slight phase difference between electron and hole. If for length equals 0, it doesn't matter. And it's usual to take the Andreev approximation also to say that they are at the Fermi wavelength. Yes.
In the leakings, substitute aluminum leakings,
Yes.
how magnetic field could influence the Andreev bound states? Would it just vanish?
Yeah. Very good question. So it depends on the intensity of the magnetic field. So the magnetic field is very large, you kill superconductivity, and then you kill Andreev states. This is one possibility. If you put small magnetic fields, then there is a Zeeman contribution, but this Zeeman is very small. It's of the you need, to see some splitting of Andreev states, you need large fields, and this is normally very hard because of what I've said before. There are other strategies to get an effect of magnetic fields on Andreev states, to get some splitting, which relies on different ingredients. I can comment on this. But it's another cuisine.
I would like to know how did you measure the pressure when you show the first slide?
The compression.
Yes.
See, there it's just stated in micrometers, so which is just the calibration of the pusher. We don't know this. We can estimate, but essentially the aspect ratio of the suspended bridge is what gives the demultiplication factor to go for micrometers to Armstrongs. But I don't know the compression. It was a compression in micrometers, just indicated.
So you have compared the curves which you obtain in a single atom point voltage with a curve which you obtain in a large microscopic junction.
Yes,
Okay.
this is for for
so
playing.
Did you compare with what you obtain when the system is fully separated? Because
Yes,
you
yes,
can
yes,
continue and you
this
can make
is-
a tunnel junction.
Yes, this is these slopes.
No, but
So-
when it is fully separated, then there is no current in the gap. So you have been comparing the result of a macroscopic tunnel junction with
This, I mean,
this one.
yes.
Yeah.
Yeah, just to indicate where the gap, essentially, where is the gap of the aluminium,
My question is,
and the other facts that appear at multiples of, well, multiples,
yeah,
twice over.
but you could do the same experiment that you plot there in red
Yes.
with without making a macroscopic tunnel junction, just by moving a little bit further your pushing system and go into the tunneling.
Okay. I know what you mean. Like to go to this.
Indeed.
Yeah. Well, I have to. Yes. What I can say is, it's very hard to because this tunnel limit is. It's like you have just broken your last atom, and this is not very stable. I mean, the system is stable when you have a bonding. Even one atom bond can just be stable enough. If you don't have anything, then you will just variate. I don't. That's the last condition. I mean, you are really like almost completely open.
Okay, Peter?
You say that once
Yes.
there is a real junction, then this is very stable.